Hello everyone. So in these next few videos I'm going to be talking about something called the Jacobian. And more specifically it's the Jacobian matrix, or sometimes the associated determinant. And here I just want to talk about some of the background knowledge that I'm assuming. Because to understand the Jacobian you do have to have a little bit of a background in linear algebra. And in particular I want to make sure that everyone here understands how to think about matrices as transformations of space. And when I say transformations, here let me just get kind of a matrix on here. I'll call it 2, 1, and -3, 1. You'll see why I'm coloring it like this in just a moment. And when I say how to think about this as a transformation of space, I mean you can multiply a matrix by some kind of two-dimensional vector, some kind of two-dimensional xy, and this is going to give us a new two-dimensional vector. This is going to bring us to, let's see, in this case, it'll be, I'll write kind of 2, 1, -3, 1, where what it gives us is 2x plus -3 times y, and then 1x plus 1 times y. Right? This is a new two-dimensional vector somewhere else in space. And even if you know how to compute it, there's still room for a deeper geometric understanding of what it actually means to take a vector xy to the vector 2x plus -3y and 1x plus 1y. And there's also still a deeper understanding in what we mean when we call this a linear transformation. A linear transformation. So what I'm going to do is just show you what this particular transformation looks like on the left here, where every single point on this blue grid I'm going to tell the computer, hey, if that point was xy, I want you to take it to 2x plus -3y, 1x plus 1y. And here's what it looks like. So let me just kind of play it out here. All of the points in space move, and you end up in some final state here. And there are a couple important things to note. First of all of the grid lines remain parallel and evenly spaced. And they're still lines. They didn't get curved in some way. And that's very, very special. That is the geometric way that you can think about this term, this idea of a linear transformation. I kind of like to think about it that lines stay lines, and in particular the grid lines here, the ones that started off as, kind of vertical and horizontal, they still remain parallel and they still remain evenly spaced. And the other thing to notice here is I have these two vectors highlighted, the green vector and the red vector. And these are the ones that started off, if we kind of back things up, these are the ones that started off as the basis vectors, right? Let me kind of make a little bit more room here. The green vector is 1, 0. 1 in the x direction, 0 in the y direction. And then that red vertical vector here is 0, 1. Right? 0, 1. And if we notice where they land, under this transformation, when the matrix is multiplied by every single vector in space, the place where the green vector lands, the one that started off as 1, 0, has coordinates 2, 1. And that corresponds very directly with the fact that the first column of our matrix is 2, 1. And then similarly, over here, the second vector, the one that started off at 0, 1, ends up at the coordinates -3, 1. And that's what corresponds with the fact that the next column is -3, 1. And it's actually relatively simple to see why that's going to be true. Here, I'll go ahead and multiply this matrix that we had that was, see, now it's kind of easy to remember what the matrix is, right? I can just kind of read it off here as 2, 1, -3, 1. But just to see why it's actually taking the basis vectors to the columns like this, when you do the multiplication by 1, 0, notice how it's going to take us to, so it's 2 times 1, that'll be 2, and then -3 times 0, so that'll just be 0. And over here it's 1 times 1, so that's 1, and then 1 times 0. So again, we're adding 0. So the only terms that actually mattered because of this 0 down here was everything in that first column. And similarly, if we take that same matrix, 2, 1, -3, 1, and we multiply it by 0, 1 over here, by the second basis vector, what you're going to get is 2 times 0, so 0 plus that element in that second column, and then 1 times 0, so another 0, plus 1 times 1, plus that 1. So again, it's kind of like that 0 knocks out all of the terms in other columns. And then, like I said, geometrically, the meaning of a linear transformation is that grid lines remain parallel and evenly spaced. And when you start to think about it a little bit, if you can know where this green vector lands and where this red vector lands, that's going to lock into place where the entire grid has to go. And let me show you what I mean and how this corresponds with maybe a different definition that you've heard for what linear transformation means. If we have some kind of function L, and it's going to take in a vector and spit out a vector, it's said to be linear if it satisfies the property that when you take a constant times a vector, what it produces is that same constant times whatever would have happened if you applied that transformation to the vector not scaled, right? So here you're applying the transformation to a scaled vector, and evidently that's the same as scaling the transformation of the vector. And similarly, second property of linearity is that if you add two vectors, it doesn't really matter if you add them before or after the transformation. If you take the sum of the vectors, then apply the transformation, that's the same as first applying the transformation to each one separately, and then adding up the results. And one of the most important consequences of this formal definition of linearity is that it means if you take your function and apply it to some vector, xy, well, I can split up that vector as x times the first basis vector, x times 1, 0, plus y, let's see, y times that second basis vector, 0, 1. And because of these two properties of linearity, if I can split it up like this, it doesn't matter if I do the scaling and adding before the transformation, or if I do that scaling and adding after the transformation, and say that it's x times whatever the transformed version of 1, 0 is. And I'll show you geometrically what this means in just a moment, but I kind of want to get all the algebra on the screen. Plus y times the transformed version of 0, 1. 0, 1. So to be concrete, let's actually put in a value for x and y here and try to think about that specific vector geometrically. So maybe I'll put in something like the vector 2, 1. So if we look over on the grid, we're going to be focusing on the point that's over here at 2, 1, and this particular point. And I'm going to play the transformation, and I want you to follow this point to see where it lands. And it's going to end up over here. Okay, so in terms of the old grid, right, the original one that we started with, it's now at the point 1, 3. This is where we've ended up. But importantly, I want you to notice how it's still 2 times that green vector plus 1 times that red vector. So it's satisfying that property that it's still x times whatever the transformed version of that first basis vector is, plus y times the transformed version of that second basis vector. So that's all just a little overview, and the upshot, the main thing I want you to remember from all of this, is when you have some kind of matrix, you can think of it as a transformation of space that keeps grid lines parallel and evenly spaced. And that's a very special kind of transformation. That is a very restrictive property to have on a function from 2D points to other 2D points. And the convenient way to encode that is that the landing spot for that first basis vector, the one that started off 1 unit to the right, is represented with the first column of the matrix, and the landing spot for the second basis vector, the one that was pointing 1 unit up, is encoded with that second column. If this feels totally unfamiliar or you want to learn more about this, it's something that I've made other videos on in the past. But in terms of understanding the Jacobian matrix, where we're going with this, and kind of getting a geometric feel for it, that short overview that I gave should be enough to get us going. So with that, I will see you next video.